Good afternoon, everyone. The topic for my presentation is artificial intelligence in medicine. And almost in recent years, this is almost like a buzzword. It is almost involved in every aspect of our life. Knowingly or unknowingly, every day we are actually experiencing or witnessing the applications of AI. So, what is this technology all about? And particularly in healthcare and medicine, how the impact is being created and what is the future? That is what we are going to see in the next 20 minutes. So, to begin with, what is artificial intelligence? In simple words, we can say that it's a science of making machines to think like humans. By machine, I mean computer or any device prefixed by smart, like a smartphone, smart watch, and so on. So by think like human, I mean some decision making capability has to be incorporated onto the machine, and for that, the intelligence possessed by the human has to be translated onto a machine. So on the onset, we can say it is going to mimic a cognitive action of human being. So, though the technology, this word is very popular in recent years, it's not a newer technology. Its inception dates back to 1950s. But at that point of time, it was not so popular. I'll say the reason shortly. And in early 1980s, again a subset of artificial intelligence technology called machine learning with a very tricky programming concept, it started flourishing, and even then it was not so popular. It was in the past 1 decade, to be exact, in 2012, the technology has witnessed a great breakthrough, and with the subset of machine learning called deep learning, the technology has created a revolution in many aspects, many domains. So this is what we are going to see. So for that, as I already mentioned, there is a process called translation. Intelligence translation involved. Intelligence translation from human to machine is involved in making a decision. And to understand what is that, I'm just taking an example, a simple example of a patient approaching a doctor to get diagnosed with a disease, a dengue or not. So I'm just considering some 5 symptoms the doctor is going to examine. I'm not sure whether these are the symptoms of dengue, just for understanding purpose I've taken. So the doctor is examining the patient for skin rash, fever, headache, cold cough, and vomiting, and then he'll make a diagnosis. So the first patient approaches, he has skin rash, headache, and vomit, no fever and cold cough, and the doctor is making a decision or a diagnosis that dengue is not there. Now the second patient with all symptoms except cold cough, he approaches, and the diagnosis is made in favor of that dengue is there. And how this diagnosis is being done? It is from the past experience and the knowledge he has gained over a past experience, this decision is being done. Now, the this intelligence possessed by the doctor, that is the human expert, has to be translated onto a machine, and that's how it is going to be translated, we are going to see. So I said during the inception of the technology, it was not so popular. Why it was not so popular? We'll just see. So an expert system was devised. Expert system in the sense a computer programming based concept, it was devised. So based on the symptoms and the rules, the diagnosis will be done, and that is being translated into a computer program, a software program. So some conditions will be checked. If fever exists and fever temperature ranges from so and so Fahrenheit, all those things will be checked. We will write the software engineer or software programmer will write for some rules and then come out with the output. This is the original AI-based coding that was developed in. And what is the limitation and why it was not so popular? If instead of 5 simple symptoms, if you have more and more number of symptoms, so the rule will become more complex, and ultimately we may not come out with a greater accuracy, just like Ebola or other flu what we are currently facing. So that is the limitation of the traditional programming, AI-based programming. So to overcome that, I said in 1980s, with a tricky concept, machine learning evolved or flourished. So what is that tricky concept? Let us see. So to make a intelligence translation, like how a human will make a decision, that has to be translated onto a machine. What we are going to do is, machine learning tends to learn from the past experiences. So we have to collect the data of past records of the patient who have approached the or visited the hospital for getting diagnosed with dengue. So collect all the patient's data, 100 and 1000 and 10,000 data we have to collect actual database. So here, for example, I have just shown 4 patients' data, 1 row for every patient. Just mark the symptoms if they had and also the diagnosis, whether dengue was there or not. Now we have to translate this into a form that can be understandable by the machine, means a computer. So it's replacing all the tick marks and by 1 and cross marks by 0, not necessarily 1 and 0, any format we can change it. And then here, next what we have to give is, together with the input and the output. Please look at here that all the symptoms and also the diagnosis is being given to the system, given to the program. As input, we are giving all the symptoms. In machine learning concept, we call this as a features. So all the features and together with the ground truth, which is the diagnosis, that is being given to the system, and it is the headache of the system. It is given to a program, and it is the headache of the program to formulate the rule between to map the input and the output. Just we formulate the rules from the inputs and outputs. So this is a summary of what I was saying so far for the past 10 minutes. So the general or the traditional programming involves give the data, frame the rule, come out with the output. But the tricky programming concept involved in machine learning is give the input, the data, and also the output. Here in the data is nothing but the symptoms and the output is nothing but diagnosis. Now the machine learning model, it will come out with the rules. So this was the breakthrough that has done by the machine learning in AI technology. But still it was not so popular in 1980s. Again, we'll see the reason. What is the reason? Very shortly we'll see. And this is the basic block diagram of a machine learning model, we can say. So it actually consists of 2 phases. One is the training and the other one is the testing or the prediction phase. So in the training phase, as I said, we have to give past data. Right? The data can be in many formats. So here in this example, I have taken the image for brain MRI images. Okay. Along with the data, just for every image associated with a label. Label is nothing but the diagnosis, whether it is a benign or malignant tumor. Not necessarily only 2 cases. You can go for many number of cases, like 4 ground truths and so on. So from every images, we have to extract certain features. Just compare this with the example I have said. So previously the data was the patient. From the patient, the doctor was examining the symptoms. So likewise, from the images, we have to extract certain informative patterns from the images, and those are called the features. From the features, together with the corresponding label or the ground truth, has to be given to the machine learning algorithm, and it will come out with one model. It will come out with one hypothesis. So that hypothesis is equivalent to the knowledge or the intelligence possessed by the doctor or any human expert belonging to the domain. Now, if it is a healthcare, the expert is going to be a doctor. Now, in the second phase, if we give out unknown images of brain tumor images, the same set of features will be extracted, and from the knowledge it has gained over training, it will make a prediction that the new image which is given for testing is either benign or malignant. This is how a machine learning model will work. Okay. Now, what are the commonly extracted features from images? May it be CT images or MRI or PET scan, whatever it is. Some of the commonly used features, shape features. What is the area of the tumor? What is the boundary, whether it is regular or irregular, and so on. And some statistical features, mean, median, and so on. Then Text features, very popular features. These are some of the parameters denoting the quantifying the texture of the image. Then comes the color features. Now these are not the only features. These are some of the features, and most commonly used is texture features. So for example, I have taken a liver images. Liver first two images belong to the category of hepatocellular carcinoma, and this is a hemangioma. So I have extracted some features, some sample for texture features from the normal healthy portion of the liver and the HCC tumor portion of the liver, and this is the hemangioma tumor of the liver. So they possess different ranges of values. So this is an example for features what we are extracting from the images. Now comes what is the limitation of machine learning. So the heart of the machine learning is feature learning or feature engineering. So irrespective of what is the input, we are actually worried on, we are actually feeding input as the features as the input. Right? So if I extract different set of features, my accuracy level or my prediction accuracy will change. So the accuracy of prediction is totally dependent on what sort of features I am extracting. But to make it uniform, we are going for another subset of machine learning, which is called deep learning. And why this deep learning has made a tremendous breakthrough is the algorithm is formulated in such a way that how we human are making a decision, in a similar way the computers will also make a decision. How the information is processed by the brain in a human, in a similar way the information are going to be processed by the computer algorithm. So it is almost, its task is almost to mimic a brain, right? It is not 100% to some extent we are saying. So this is what is deep learning. So in machine learning, just an example of checking whether this image is a car or not. From the car, we have to extract features. What might be the feature? What is the shape of the car? What is the weight of the car? How many wheels are there? How many doors are there? Something like that we have to extract, feed into a machine learning model and come out with a car. Similarly, for deep learning, we need more from the images. We will not extract any features, but the algorithm itself will extract the feature and perform the classification. That is what is the difference. Now, so far I was saying machine learning was not so successful when it was inception, but now it is so successful. What is the reason? So here, as I think you would have understood that this machine learning is a data thirsty algorithm, which means we need to give more and more past experience, past data. So at that point of time, I don't think very PACS and EHR were not so famous at that point of time, and we didn't have sufficient memories to store all the patient's data. But now storage devices are also available, and at low cost or at free of cost, we have cloud resources to store the data. So this is one of the reasons why the technology is facing a revolution at this point of time. And the next one is to process the huge volume of data. A simple CPU might not be sufficient. So I need a very high-end GPU. So it is, yes, of course it is costly, but now even we can hire the GPU, that is the GPU from Google or other technology giants. We can hire it in a cloud from their cloud access, and then we can process our data. So that is possible currently, but not in 1980s and all. So what are the different types of data that can be worked on it? The data can be a tablet data or a text or an image or a video or some signals. So on that we can work. So the basic inspiration, I was saying deep learning will work in a way similar how human brain is working. So on the left side we have one single biological neuron and a network of neurons. So here, in a way, how the single neuron is passing the information from one neuron to another. It will collect the information from dendrites and pass through the axon terminals to another neuron. In a similar way, the mathematical neuron is being formulated, and this is the neural network shown over here. You have the interconnection of different neurons at one layer and different layers and so on. So here, like if we human are just watching a scene from the retinal nerves, how it reaches the brain, the center deep into the brain. through a network of neurons. In a similar way, it will be transferred from the input to the central processing unit of the deep neural. There are many architectures available. Convolutional neural network, it was the very first architecture that made the technology of artificial intelligence into the limelight exactly in 2012 with the AlexNet architecture. And there are other architectures available, recurrent neural network, autoencoder scans, and so on. So I said, in a similar way, how we are making a decision or we are viewing an image, in a similar way, deep neural networks will also view the image. So for this example, I've taken a face recognition dataset images. So how we will see, we are just looking at a person. From the retinal nerves, the information will be transferred deep into the brain, and then some interpretation will be done in the brain, and we will understand who is the person standing in front of us and what is hidden. So in a similar way, we have a network of neurons. In the initial layers of neuron, the edges and the lines, all those things present in the images will be seen. And this will be transferred to the next layers of neuron, and combine all these edges and lines will be combined, and a representation of the a part of the image, like an organ, nose, eyes, and those will be seen in the middle layers. And these organs, when it is fed into the other, passed on to the other layers of the neural network, the abstract representation of the face will be formed, and this is how the computer is viewing at the faces in the images. This is an example. Likewise, for all the images, this sort of representation will be being done in this particular architecture of CNN, convolutional neural network. So now with this introduction, let me move on to the applications of deep learning in healthcare. So I have taken different modalities. The first modality is medical imaging modality I have taken. And under that category, the first application is classification. So from three different scenarios I have given. One is the liver cancer classification, then lung nodule and lesions. So we have to give sufficient amount of images for training along with the ground truth. Then after training, we have to do the testing. If you give any unknown images, it will come out with the output. It will come out with the prediction whether the image under test is being, whether it is HCC, hepatocellular carcinoma, or intrahepatic cholangiocarcinoma, and so on. So the accuracy is basically dependent on two things. What is the quality of the data you are giving, volume of the data, and along with the proper ground truth. If the database what we are giving is not proper, if it is not sufficient, then the accuracy may come down. So this is classification. Technically, I basically belong to engineering domain. This classification is a technical term for this sort of application. I hope you can understand the computer-aided diagnosis. Next one, the second application is detection or localization. Once if I am very sure that this image belongs to a tumor category, where exactly the abnormality is there, we have to spot out the abnormality, and that is called localization or detection. So here, with the help of bounding box, where the abnormality is there is being highlighted. I think here the blue ones are the ground truth and the red one is the predicted one, right? So for the chest X-ray and the mammogram and another limb X-ray, the localization example is being shown. And this is another project of work of Google AI healthcare research team called LINA, lymph node assistant. So from the stained histopathological or the tissue samples, where exactly the abnormality is there, that is the metastatic breast cancer tumor, from the lymph node biopsy, it is being identified, presented over here. And they have claimed that with 99% of accuracy, their system LINA is able to spot out the abnormality, that is the metastatic breast cancer tumor. Now we have spotted out where exactly the abnormality was there. But I want to trace the exact, instead of giving a bounding box like thing, I want to have exact shape of the or exact boundary of the region of interest. I have taken an example of liver segmentation over here, and I hope you may understand that over a CT series, the shape of the liver, shape, dimension, and volume of the liver, shape and dimension of the liver vary very well. and I want to go for segmentation of liver from every single slice of CT. So the traditional image processing based segmentation algorithm may not work out here. So we have to go for AI based algorithm. So for every image, I have to create a ground truth training. So this is the image and this is the ground truth for liver. Wherever white color is there, which means that portion in this image belongs to liver. So this is the tumor ground truth. Wherever white is there, that portion in this image is a tumor. And the ground truth for 3 vessels, hepatic vessels, are presented over here. So we have to feed the image, input and the output. Input is the CT image, output is the ground truth image. So feed in, do the training and come out with the segmentation for unseen data. Unseen in the sense the images which are not given for during training. So once if I'm able to segment data, liver or tumor or the vessels from every single slice of CT, then I can go for 3D reconstruction of CT images. So here we have done a 3D reconstruction of liver and portal vein from the CT, from the radiology images. And one another application, this is a published work. So after segmentation and 3D visualization and volume calculation, so prior to the actual radiation therapy for a patient, the physicians were assisted in finding out the amount of radiation required for a patient. So this is one application. Another application here is to reduce the risk associated with contrast injection in the image acquisition. So here the left side, it's a standard dose contrast, gadolinium based contrast dye is injected, and this is the standard dose. So there is a very clear discrimination between the tumor and the other part of the brain. Because with a very mild dose, there is no clear discrimination. So using the deep learning technology, from having this as the input and this as the output, this as the low dose as the input and the high dose as the output, train the model and come out with this model. So if this is possible, then no need to go for the image acquisition with a standard dose of contrast. Then we can just go with low dose and process it. Finally, we may get this particular image. So not necessarily with images. The second modality I'm considering here is signaling. So we have for any of the physiological signals like electrocardiogram, EEG or respiratory signal, we can go for building a prediction model based on either ML means machine learning, or deep learning. And the third modality I'm considering here is the sensor. For example, the body area network or the fitness band we are wearing, it will absorb the vital parameters. So collect the data from those sensors, process it, and find out build a model and find out whether any abnormalities is going to happen or happening. If this sensor data is connected to internet and accessed by cloud and processed, then that is called the IoT. That is what is IoT, that is Internet of Things. Internet of Even, we can call it as medical things. The fourth modality I'm just taking as the natural language processing, which means the written notes, written clinical documentation or the speech recognition. It is understanding the natural language, what is the language the patient or any human is speaking, that and translation is called the NLP. So this NLP leverages well in the clinical documentation. It will tend to reduce the burden of the physicians or clinicians in their documentation procedure or reading and making a decision from the EHR data and so on. Even it will analyze the speeches and make some processing on it. So these are some of the top use cases under the umbrella term of natural language processing. Now an example I've just taken in a cardiology, what are the AI-based tasks that can be done. And the publication, if you look at the past 15 years, the publications based on machine learning and deep learning has started. There are more and more publications in the past 10 to 15 years, only on cardiology. Now, what are the different applications? Some of the examples. So, starting from all modalities, echocardiogram, CT, MRI, angio, ECG, and even from the clinical data, many different AI models were done, and all these were published. And even not only finding the diagnosing of the disease, even we can predict in future what is the event. and after some 2 or 3 days, is there any possibility for heart failure, or is there any possibility for readmission? If the patient is getting recovered, and is there any possibility to get the worst condition in future? All those things are also possible and are also recorded and are published in literature. So many technology giants like IBM, Google, they are investing, Microsoft, they are investing more and more onto AI. Tesla is investing more on self-driving cars. Likewise, so every technology company they are investing more onto the AI, particularly for AI, healthcare AI. So some sample research outcomes for the Google research team, the Google AI research team that is named as Google Brain. So a wing of the Google research DeepMind, they have in 3-4 years back, they have come out with an outcome that AI technology can spot acute kidney disease 40 hours before the actual happening or before the doctor spot. And after from the clinical data of the patients, with the they have identified that 76% chance of readmission of the patient in the hospital. That is also prior 24 to 48 hours in prior they are able to predict it. And one another research on the diabetic retinopathy in in field work with Aravind Rai Hospital and Shankar Netralaya. What in addition to finding out the research on diabetic retinopathy, so they have also got more and more insights from the images of retina. There is a possibility of predicting cardiovascular disease. That is also possible. So these are some of the Google research we have shown. So the advantages, all these are advantages. They are able to assist in the clinical processing. But what is the lacuna of the deep learning? So when it is coming out with a high accuracy, but what is the reason it is coming out with this diagnosis? That explainability is lacking. So initially the AI-based technology was rule-based. We are writing some rules and coming out with the output. In that time, the accuracy was less, but I am able to interpret or give an explanation why this decision is being made. But now the deep learning models are coming out with huge accuracy, very good accuracy, but the reason behind the diagnosis or the decision is not known. So it lacks interpretability. So it is almost functioning like a black box. What is happening inside we could not know. So without knowing that, particularly in healthcare system, we could not rely on those AI models. So to overcome that also, explainable AI technology is recently an active area of research in the field of healthcare. What is this explainable? Whatever decision I make, I should be able to provide a explanation. For example, if my model says this is a cat, why it is saying it as a cat? I know this is a cat, but the model should also come out with an explanation why this is a cat. For example, it has whiskers, fur and claws, so it is making a decision that it's not a dog and it's a cat. So on top of the existing infrastructure, some interpretability module has been stacked on top of the existing. So what sort of interpretation it will provide? Some sort of visual interpretation, not written explanation. The explanation will be some sort of visual explanation. What is that visual explanation? Let's see. So if my machine learning model or deep learning model is making a correct prediction that this dog belongs to the breed of golden retriever, why it is making such a decision? Why it says that it belongs to a golden retriever and not some other brand, some other breed. So here it will come out with some heat map like image. On overlapping that heat map like image onto the original image, wherever the red portion is there, that is the strong focus where the network is looking at the image. So it is on looking at the portion above the eyes and the folding of the ear, it is making this decision. Another example, this is correct decision that this is a shoe is being done. But why this is decided as a shoe? On looking at the tapering portion of the shoe and the place where we will insert our leg, they are the red colored ones. So these are the regions that is contributing more into the decision that this is a thing. These are different algorithms. I don't want to go into. Now coming to the healthcare, this technology is being, this explainable AI is being deployed. So once if we know the diagnosis is the reasoning behind the diagnosis, then we can decide whether to rely or we can trust this system or not. Or suppose if the diagnosis is wrong and what we are able to know what is the reason, we can do some correction onto it. So here this is deployed in COVID images and also in Alzheimer disease prediction, COVID X-ray, again COVID X-ray, mammogram images and so on. Again, what is the drawback of explainable AI? There is actually no ground truth. It is giving an why I make this decision, it is giving some sort of visual explanation. But only an expert can interpret whether this explanation is correct or not. There is no ground truth for this. So again, this is the drawback. And towards the conclusion, what is the research challenges associated is we need the huge volume of data. With very few data, if you are training, then the accuracy may come down. Only the accuracy may go up only if you have sufficient more and more volume of data. Data in the sense CT images or signal or whatever it is. And if you have sufficient more volume of data, I need a high-end GPU to train the model. It may take days and hours and days and even weeks time to get trained. And another important challenge is ground truth preparation. Ground truth, what we are associating with every image or signal, if this is not properly prepared, the entire learning will go wrong. Okay, this is a time-consuming work and it has to be prepared only by an expert. In field of healthcare, the expert is the clinicians. And to conclude, human intelligence. Normally, the clinicians or radiologists, they very well make a diagnosis, but there are some cases where there is a possibility to miss certain diagnosis. It may go unnoticed to their naked eye. In that case, machine intelligence give a handshake. They may identify those misdetected one, but they may overperform. They may introduce some false positive. So when both the intelligence, machine intelligence and human intelligence are brought into synergy, then the false positive may be reduced and the algorithm, DL algorithm will reduce the missing tumor cases. Then ultimately, together the human expert and the AI technology, the enhancement, the performance will be better than the individual's one. So to conclude, the robust algorithms. The algorithms should be very, very strong enough. The rules, the data should be very prompt data. There should not be any error in the data and all. And with providing the interpretability and the most important one, human expert in the loop, we can make an AI model into a trustworthy AI model. So it is the thing is all the data scientists and the technology is not a single-ended technology. It has a technologist and also the domain expert. As far as healthcare is concerned, the data scientist and the clinicians, they should work in synergy. Only then this will come out with the meaningful models, prediction model. So I end my presentation over here and I am glad to answer if there are any questions.